Hello, this is Monique Morton, Mathematics and Computer Science Content Director for Advanced Kentucky. And in this video, I'm going to talk about optimization problems in calculus, focusing on all of these problems have to do with motion along a line. So in my first example, a particle moves along the x-axis such that its position at any time t, where t is on the closed interval from 0 to 5, is given by the function x of t is equal to 12 times t minus 3 to the 2/3 power. We're asked at what time t, where t is on that interval, is the particle farthest to the left. Well, since we're moving along the x-axis and the x of t function is given position, it's actually giving us the x-coordinate on that axis, and we want to find the smallest x value. Right? When we move farthest to the left, we'll have the smallest x value. So really this position function, x of t is equal to 12 times t minus 3 to the 2/3, is the value that I want to optimize, in this case, minimize. I want to minimize x of t. So I need to do an analysis using a first derivative. Okay? X prime of t is equal to, let's see, 8 times t minus 3 to the minus 1/3 power. Okay? Now, I'm going to write this as a fraction to make it easier to see. Okay? This first derivative is never equal to 0, right? This is never equal to 0 because this numerator is 8. Okay? So this is never going to be equal to 0. However, there is a critical point at x equals, or rather t equals 3. So now that I have my critical point, I'm going to go ahead and use the first derivative to determine whether that's a max or a min, or neither. So I'm just going to do this way. X prime of t is negative when t is less than 3, right? If I put in a number smaller than 3, I get a negative number in the denominator, and the numerator is always positive. And x prime of t is always positive when t is greater than 3. Actually, let me write these intervals as 0 less than t less than 3 and 3 less than t less than 5, right? Because I'm on the interval from 0 to 5, and that takes care of my entire domain. Okay? Since the sign of the first derivative, since x prime of t changes between negative and positive, changes from negative to positive at t equals 3, x of t is a minimum. I-M-U-M. When t is equal to 3. So therefore, the particle is farthest left when t is equal to 3. Okay, so that's a perfectly good justification for the optimization problem. I started here by finding the first derivative and the critical points. And this part, I'm doing the first derivative test. And right here is where I'm pulling it all together. Now, just for expoundment, or to note, this is not the only way to do the problem, right? Here I used the first derivative test, but I could start at this point right here and go into the candidates test, right? It's a closed interval, so really I could find the position at 0, the position at 3, and the position at 5 and pick out the minimum from there. Since I only had one critical point, I test that's a candidate, and the endpoints are candidates because this is a closed interval. So 12 times 0 minus 3 to the 2/3 power, that's 12 times 9 to the 1/3, right? If I square -3, I get 9. 12 times 3 minus 3 to the 2/3, that's just 0. Okay. And 12 times 5 minus 3 to the 2/3, that's 12 times 5, well, 25 to the 1/3, right? So it's clear here as I'm doing the candidates, testing the endpoints and the interior critical point, that this value here is the minimum. So I would wrap that up that way. Therefore, there's a minimum. I could attempt to do the second derivative test. I do have a critical number. When I try to do the second derivative test, I'd see it and do the second derivative test. I would need to do the second derivative first, right? At negative x over 3 times t minus 3 to the negative 4/3 power. And let me write it this way so that it's clear that I cannot evaluate x double prime of 3. Okay? And the reason I can't evaluate x double prime of 3 is because it's undefined, because 3 makes the denominator of this expression 0. Therefore, the second derivative test doesn't apply. Now, I could have stopped and not even attempted it if I realized that back here at the top, my critical number occurs when x prime of t is undefined, not when x prime of t is 0. And so the second derivative test is only going to work when x prime of t is equal to 0, when we have that sort of critical point. So I've looked at 3 different ways to solve the same problem. Let's look at a new problem. Again, all of these problems have to do with particle motion. So in this example, a particle moves along the x-axis such that its position at any time t, where t is between 0 and 10, is given by the function x of t is equal to 6 times t minus 6 to the 1/3. At what time t, where t is between 0 and 10, is the particle farthest to the right? Now, since we want to know when the particle's farthest on the right and is moving along the x-axis, we want to find the maximum value of x. So we have our optimization equation. This is the equation for x that was given to us, so we don't have to find it. And then finding the first derivative, x prime of t is equal to 1/3 times 6, 2 times t minus 6 to the negative 2/3 power, which if I write this way, because that might be easier for some of you to see, means that x prime of t is never equal to 0, so it doesn't have any critical points from that. But it does have a critical point where t is equal to 6. Critical point when t is equal to 6. So if I go ahead and do the first derivative test, which is most of my first instinct is to do the first derivative test. I tend to do that or the candidates test, but I'm going to start out with the first derivative test here. And I notice that if I look at the sign of x prime of t for numbers of t smaller than 6, it's going to be positive when 0 is less than or equal to t, which is less than 6. And it's also going to be positive, right? Putting in numbers bigger than 6, that's being squared first and then taking the cube root is one way to think about it. So they're going to be positive when t is between 6 and 10. Right? So here's my analysis of the first derivative. Notice that there's no sign change. It's positive on both sides. That means that it's neither a maximum nor a minimum. So there is really no point in me moving on with that point. In other words, the answer occurs at one of the endpoints. And since it's positive here, that means that x of t is increasing. And it's positive, it being the derivative. On that interval means x of t is increasing again. That would mean that I'm farthest to the right when I'm at the rightmost endpoint. Okay. The particle is farthest right when t is equal to 10. So sometimes, even though we have a critical point, we don't have a sign change, which means that that critical point is neither a max nor a min, and we have to look elsewhere. In this case, since it was a closed interval, we checked out the endpoints. As a side note, I could have gotten the same answer by using the candidates test, even though I already know that that's not going to be the answer when I do the sign analysis. If I do the candidates test, I'm not going to do a sign analysis. I'm just going to evaluate at 0, at 6, and at 10. And it doesn't take too long. This is 6 times negative 6 to the 1/3. That's small. This is 6 times 0 to the 1/3. That's 0. And that's 6 times 4 to the 1/3, which is a positive number. This one's clearly the maximum, and when the particle is farthest to the right, even when I do the candidates test. So I have one more example to look at before I wrap up this video. This time the particle is moving along the y-axis. So we're going to think that just like along the y-axis, the further up you go, the higher or the greater the value of y. The further down the y-axis you go, the smaller the y value is. And that's where your negative numbers are. So that's something to keep in mind. A particle moves along the y-axis such that its position at any time t between 0 and pi is given by the function y of t is equal to 2 plus t sine t plus cosine t. At what time t, where t is on the closed interval from 0 to pi, is the particle at its lowest point? So since this is my position function and I want to maximize, no, actually, I want to minimize the lowest point. So I want to minimize the position function. Here is my y of t function, writing it over again. And first, let's take the derivative because we'll need that to determine critical points. Oops, t. So the derivative of 2 is 0. We need the product rule to do the derivative of t sine t plus t cosine t. And then the derivative of cosine t is negative sine t. Notice that these two sine t's add to 0. So y prime of t is t cosine t. Now, this function is not undefined anywhere, but it will be 0 somewhere. So we kind of need to know, when is y prime of t equal to 0? Well, we could probably do this by hand. I'd rather do it by using my calculator. Here's a graph from what my calculator says. And notice these are x's instead of t's. But anyway, this is graphed on the interval from 0 to pi. And I found the point of intersection, which happens to be exactly pi over 2. In fact, if we think about putting pi over 2 in for t here, right, pi over 2 times the cosine of pi over 2. Cosine of pi over 2 is 0, so the product is 0. So on the interval from 0 to pi, y prime of t is equal to 0 when t is equal to pi over 2. So looking at this value, I'm going, okay, t equals pi over 2. Let's talk about using the first derivative test. Again, that's usually my first instinct. So my first instinct is at t equals pi over 2, and therefore y prime of t, since I graphed it, I can just look at the graph and determine the signs, right? So y prime of t y prime of t is positive for values of t between 0 and pi over 2, and y prime of t is negative for values of t between pi over 2 and pi. So that would mean that I have a relative maximum at t equals pi over 2. Okay. So since that's a relative maximum, it clearly is not going to be the minimum. So the minimum must be at one of the endpoints. So checking the endpoints, y of 0 is equal to 2 plus 0, right, because t is going to be 0, plus the cosine of 0, which is 1, so y of 0 is equal to 3. And y of pi is going to be equal to 2 plus pi times the sine of pi. Well, the sine of pi is 0, so that's 0, plus the cosine of pi, which is negative 1. So this is going to be equal to 2 plus negative 1, which is 1. And therefore, the particle is at its lowest point. The particle is at its lowest point when t is equal to pi. It's very important to check those endpoints because in this case, the value we wanted was at the endpoint of the interval. I hope this was helpful in looking at optimization problems that are set in a context motion along a line. This is Monique Morton. Have a great day.